Alright, hey everybody, my name is Tyler, and I'm going to be walking you through the FEA Trust Optimization in MATLAB project that I completed for ME 548 Design Optimization course throughout grad school. First thing you're going to want to do is download this zip folder here. I'll download that. Those are all the MATLAB files. Then you can go up here to your downloads folder, and this is a compressed zip folder. We're going to want to click on that and then extract all. So unzip this, extract. In the meantime, you're going to want to open MATLAB. Here we go. We'll get MATLAB running here. And here we go. Now we've got our unzipped folder. We can go ahead and delete the zip one. Next, you're going to want to navigate to your downloads folder for MATLAB. So I'm going to go to downloads here. Here we see the MATLAB Design Optimization folder. ME 548 is the class. Here we have the design optimization software. Some of this was provided, classes, function calls from my professor for completion of the course. Some of these scripts were written by me for several homeworks and things like that. So this we don't need to worry about going into. And then here we see the project folder. We are going to need access to the design optimization software scripts to run the code in the project. So what you're going to want to do is just right click on this and add to path selected folders and subfolders. That will add all of the files to the directory for the computer. Then we're going to want to go into project, and we've got final files. We'll open up all of these. You don't need to open this matrix number 9585. That's actually the final bridge design that my partner and I submitted for grading. That's our optimal design. So I've just got all these. Let me get them ordered here for you, and I'll walk through them. So the next thing we're going to want to do is just talk about how this project works. All right, so the first step was to create truss design, bridge designs that meet the geometric constraints. So we've got a constraint on the length of the beam members, 10 meters. It's a 100-meter bridge, but each member can only be 10 meters long. There's some void space where we cannot put truss members, and there's also a rule where no members can cross, so they have to only intersect at joints. So what this code does is it generates random truss designs that meet all of those geometric constraints. It won't return a design unless it meets those geometric constraints. There's some nodes, some coordinates here that are hard-coded, such as the perimeter and outline and some additional void space, just to give us more structure to our random designs in certain ways that we seemed to match up with the Warren-style truss. So that helps the measure create design. So if I run this here, you'll see we get an image, the geometry for a random truss design. You can see kind of the hard-coded perimeter that we're always going to get. You see the blue space is our operating space where trusses are allowed to be created. White is void space, so we can't go in these void space. You'll see these additional triangles here, so we created additional void space to mimic that Warren-style truss and give some more material that can be reallocated to other members. You'll see the isotropy. The random design is mirrored horizontally across the center axis, the central y-axis here. And every time I run this, it takes a little bit of time because that's to find one that meets all the constraints. You get a random design. So every time you get a random design, and they all meet this one parameter. We didn't change the parameter for the scope of this project. So the next thing I did was turn this into a function call, that measure, where now it can be called in a driver file. So it's the same thing, just with a function call, and its inputs are grid density and nrand_i. That is the grid density. If I open this here, there's a certain uniform density for the nodes. It's hard to see in this one, but you can kind of see it along the top here. Every 10 meters there's a node, and having a uniform grid density helps the measure find geometries that meet that 10-meter length constraint. If the grid density is too high, it struggles to find designs that meet the constraint. Too low, you get too many nodes, and the bridge isn't that good. The next input is the nrand_i. That's the number of random internal nodes. So if I run this again, you see there's some of these that are just in random locations. Increasing the number of random internal nodes just adds more random internal nodes in this space, and less with less internal random nodes, you get more of a uniform grid density look. So playing around with those can greatly increase or decrease your compliance, your deformation in the bridge, and that's what we sought to study here. Here's the algorithm created by my partner and I that actually does the optimization. The optimization being you submit a design. Here's the coordinates, the XY coordinates. That's what the measure returns. The XY coordinates of all the joints, all the nodes where members intersect, as well as the connectivity. So in what order do the members connect? You've got member 1 connects to member 3, member 1 connects to member 2, etc. So you submit the connectivity, and what this does, see, you submit the XY coordinates and the connectivity, and what this does with your volume constraint, your stress constraint, your volume being the mass, the total material, your Young's modulus, your yield stress of the material here, it will reallocate the material, so it will make certain members thinner and certain members thicker to minimize the deformation, minimize the compliance, increase the stiffness of the bridge design. That's what this does. So this is the optimization algorithm and the theory, the mathematical theory for our constraints here. You see we've actually have a couple constraints, tensile and compressive for each member. So we have to analyze tension and compression for each member and things like that. So then in the test project function here, you'll see this is hard-coded. This is actually the hard-coded connectivity and XY coordinates of number 9585, the optimal design. I hard-coded this in here just before submission to my professor, so there would be no errors with him having to, no issue with him having to open another file or input this. So this would just be easiest for him to grade. He could just click run on this script and get the final design. But what test project does is it runs this Truss 2D min compliance all constraints, so it optimizes the design given the XY coordinates and the connectivity. You input your maximum mass of the truss, 3,060 kilograms, your density of the steel, things of this nature, and what it does is it optimizes the design, and it plots the design and computes the stresses and things like that. So if I run this for our optimal design, I'll just show you here. This will show you the deformation and the results of our final design that we submitted here, and then I'll talk about how we arrived at that design. So once this completes, we'll see we have, here we go. Oops. Here we have the geometry. So this is our optimal geometry. All the red dots are the nodes. You see the connectivity, you see the load in these arrows evenly distributed along all the bottom nodes. And then this image here shows an exaggerated view of the deformation of the bridge. You've got 0.066 meters as the maximum deformation, and the volume. This volume is always the same. It's an active constraint, meaning that to minimize the compliance, you're always going to use all the steel you have. So this volume corresponds with the maximum mass of the steel, that 3,060 kilograms for the bridge. And you can see a little bit of bending in here. And then if we go down into the command window, you can see that our initial volume and our final volume are pretty much the same. Like I said, you're using all the material. You're just rearranging it through the Truss 2D min compliance all constraints code. Our initial compliance was 4.58 times 10 to the 3. Final compliance 2.329 times 10 to the 3. So about cut in half on the compliance. The stress is reduced by nearly a factor of 4 here. So then again, I turned this into a function where you pass it after the measure function generates a random design, the XY coordinates and the final connectivity. Then you plug that into this function, you pass the XY coordinates and the connectivity matrix, and this will evaluate each random design from the measure function. So then with these two functions, the measure function and the project function, we can then create a driver file here where you give it like we showed here in the measure function, the inputs in your driver file, you give it the uniform grid density of 10 and the number of internal nodes 80. What this does is this will create a folder unique to these design specifications. So it will create a folder called archive design 10_80, meaning in this folder we've got all the designs with a grid density of 10 and the random internal nodes of 80. and it iterates through this for loop, however many iterations of this loop, to create random designs. So for this instance, we would create 10 random designs here. For some of our parametric study, you'll see throughout the report that I ran a 10,000 design evaluation study. And this is in parallel. It's a pair for and a pair save, meaning that my computer, my 8-core machine, 16 threads, will run this in parallel, just quicker, and you can run and evaluate multiple designs at once. So then this saves each design as design number 1, design number 2, design blah, 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 all the way up to 10 or 10,000 in that archive design folder here. So now you've got your XY coordinates and your connectivity for all those random designs at these specified parameters. And then this design analysis script, you pass it the folder you want to investigate. So I want to investigate all the designs with a grid density of 10, 80 internal nodes. It loads up all of those, and after the final connectivity is delivered, and you see here we've got the test project function. So all of these designs actually are being tested, they are being evaluated, they are being optimized, the compliance is minimized as it rearranges. So then this design analysis script, all it does is just plot what is the maximum compliance I saw in every single design after it was optimized. So if I run this for 10 and 80, that's what I'm looking at here. So with a grid density of 10 and 80 internal nodes, I ran 10 random designs, found 10 geometries that meet. I optimized those 10 designs. I moved around the material. And here was the maximum compliance that I saw for each of those designs. So it looks like design 1 here is our best with a compliance of 2,893. That's what the command window returns. Design 1 is the best. So this is the methodology used to find. We ran several studies altering the grid density and the number of random internal nodes until we investigated how those affect the compliance, and then we ran a large study with what we found to be the best grid density and number of internal nodes, 10,000 designs at those values, and selected the minimum compliance design, which happened to be 9,585 for our final design, and that's how we arrived at this design here. So yeah, feel free to follow through the blog post below, learn a little bit more about the theory and the design process and future improvements, because I think there's a lot of ways you could further iterate this project to make it really, really cool. Thanks.